After this lesson, students will be able to solve one-step algebraic equations. Now brainstorm. What is an equal sign, and what does it mean? Pause the movie to come up with an answer to these two questions, and resume when you're ready. Now, common misconceptions are to think of equal signs as one-sided. Equal signs don't just signal when the answer is going to occur in an equation. Rather, they show that both sides of the sign equal each other. Think of an equal sign from now on as being the fulcrum of the balanced equation. The fulcrum is this piece right here, where you'd have a scale that is balanced. So for example, if I have 6 marbles that all weigh the same amount, and I have 6 marbles on the other side that all weigh the same amount, then my scale will be balanced, because 6 equals 6. Neither side is heavier or lighter than the other, and therefore it's not tilted. It's balanced. Now on this scale, notice how I have a block that is worth a value of x, along with 2 marbles. And that's balanced with the other side, which has 8 marbles. If we were to write this as an algebraic equation, we could say that x plus 2 equals 8. Therefore, x must be worth 6 marbles, because the 6 plus the 2 would give us 8 on the left side, which would be balanced with 8 on the right side. Now in algebra, when we want to figure out the value of an unknown number or variable, we can do inverse operations. As long as we do the same thing to both sides of the equal sign, both sides will still be equal. So for example, if I have a balance with 6 marbles on the left and 6 marbles on the right, the scale is balanced because each side equals one another. Now if I were to take away 2 marbles from the left side, and I took away 2 marbles from the right side, my scale would still be balanced, or my equation would still be true, because 4 does equal 4. In other words, we can do whatever we want to our algebraic equation as long as we do the same thing to both sides of the equal sign. In our next example, you'll see that I begin with 2 on each side of our balance, or equal sign. Now if I were to multiply the left side by 4, I end up with 8. If I multiply the right side by 4, I end up with 8. Since 8 equals 8, my equation still works. It's still true. So this time, we multiplied both sides by a number. And since we multiplied them both by the same number, our equation is still true. Now in algebra, we often have equations with variables. So if we can get the variable by itself on one side of the balance, then we'll know what it equals, because it'll equal whatever's on the other side of the equal sign. So for example, if I have x plus 4 equals 9, I can think of a scale that has a block of x, which is an unknown amount, plus the 4 marbles, and that equals the 9 marbles. Well, if I can get x by itself on one side, then I'll know that it equals whatever is left on the other side. So, I can remove these 4 marbles from the left, as long as I remove 4 marbles from the right. Then I'll be left with x on the left side of the equal sign and 5 on the right side of the equal sign. In other words, we took x plus 4 equals 9, and we subtracted 4 from the left and 4 from the right of the equal sign. These cancel because positive 4 and negative 4 equals 0, so I'm left with x equals 5. So again, in this example, we originally had x plus 4, and in order to isolate x, we took 4 away. In other words, we did the inverse or opposite of adding 4, which is subtracting 4. So now, let's fill in this table. On the left, we have certain operations that you'll see in our equations as we move forward. In order to get rid of these, we have to do the inverse operation. The inverse of adding would be subtracting. The inverse of subtracting would be adding. The inverse of multiplying would be dividing. The inverse of dividing would be multiplying. Now, if I have a number that's being squared, in order to get x alone, I would have to take the square root. So now let's practice. Number 1, I have m plus 37 equals 56. Well, since I have m, my unknown amount, and I'm adding 37 to it, which equals 56, I want to isolate my m, or get m alone. In order to get m alone, I do the inverse of adding 37, which would be subtracting 37 from both sides of the equal sign. Positive 37 minus 37 equals 0, so those cancel out, and I'm left with m alone on the left side. Now I can do 56 minus 37, which gives 19. So m equals 19. Now it's a good idea to check your answers, just to be absolutely certain. So if we were to plug back in 19 for m, we get that 19 plus 37 equals 56. And when I do 19 plus 37, I do get 56. Since 56 equals 56, I know that m does equal 19. Number 2, d minus 14 equals 27. Here, I'm subtracting 14 from d. The inverse of subtracting 14 would be to add 14. Whatever I do to one side of the equal sign, I have to do to the other side in order to maintain a true equation. Negative 14 and positive 14 cancel out, so I'm left with d equals, and now I can add 27 plus 14, 41. Now if I want to check this, I could plug in 41 for d and see if it's true. So 41 minus 14 does give us 27. 27 does equal 27, so therefore d does equal 41. Now number 3, we're taking our unknown amount c and multiplying 9. The inverse of multiplying by 9 would be to divide by 9, and therefore I have to do that to both sides of the equal sign. Now the reason this works is because 9 divided by 9 is 1. 1c could be written just as c, and so I did isolate my variable, which is our goal. Now I can do 126 divided by 9, and I get 14. So c equals 14. And now I want to check my work. So 9 times 14 should give us 126. Oop, 126 does equal 126, and therefore c does equal 14. Now for number 4, w is being divided by 8. The inverse of dividing by 8 would be to multiply both sides by 8. Now notice how I wrote my 8 up here, so I can think of it as 8 over 1. Now I can cross-reduce by dividing each of these by 8, which gives us 1 and 1. And when I multiply straight across, I'd get w over 1, or w. So we achieved our goal of getting w alone. Now I can do 16 times 8, which is 128. And we check our work. 128 divided by 8. Let's see if that equals 16. And it does, so our answer is 128. Now number 5 looks a little bit different. Notice how we're doing 82 minus b, whereas before our variable usually came first. Now these are slightly tricky because students often think that we're subtracting 82 and that therefore we'd have to add 82 to both sides. But really, we need to get rid of this positive 82. And the only way to do that would be to subtract 82 from both sides. If it helps, you can rearrange these terms. So circle the terms, and then switch the order. Negative b plus 82 equals 36. That might help you to visualize more that positive 82, the inverse would be to subtract 82 from both sides. Positive 82 and negative 82 cancel out. We're left with negative b equals. Now positive 36 minus 82, those are different signs, so we subtract and take the sign of the higher number. So I switch it around so that I can actually subtract 82 minus 36, which gives me 46. But I'm taking the sign of the higher number, so I get negative 46. Now negative b is the same thing as thinking of it as negative 1b. Now negative 1b is like negative 1 times b. So the inverse of multiplying by negative 1 would be to divide both sides by negative 1. Negative 1 divided by negative 1 gives us 1b, or b, and negative 46 divided by negative 1 gives us 46. So we have an answer of 46. Now to check our work, we plug in 46 to our original. 82 minus 46 equals 36. Let's make sure that this works. And it does. 36 equals 36. So b does equal 46. And now for some problems with integers. Number 1, c plus 18 equals negative 21. Well, we need to isolate our c. Since we're adding 18 to c, the inverse would be to subtract 18. And whatever I do to one side of the equal sign, I have to do to the other side. Positive 18 and negative 18 cancel, so I'm left with c. And now I have negative 21 minus 18. We think of our wrap, same signs, we add and keep. So this gives us negative 39. Now I can check my answer. Negative 39 plus 18 equals negative 21. These are different signs, so I subtract and take the sign of the higher number, which would be negative. And so that did work. Number 2, I'm isolating my f, so I do the inverse of subtracting 9, which would be adding 9. I'm left with f. These are different signs, so I subtract, which is 21, and take the sign of the higher number, negative. To check our work, I plug in negative 21 for f. Same signs, add and keep, and that does work. Now number 3, I have 6 times g equals negative 42. So the inverse of multiplying by 6 would be to divide both sides by 6. 6 divided by 6 is 1, and 1g is just g, which equals negative 42 divided by 6. Since these are unlike signs, I get a negative answer. Remember, for multiplying and dividing integers, we don't use our wrap, we use spun. So we get negative 7. So g equals negative 7, which I want to check. And 6 times negative 7 does give us negative 42. Number 4. Negative 4a equals negative 32. A common mistake here would be for students to want to add 4 to both sides, thinking that this means minus 4. But be very careful, because really what we're doing here is multiplying negative 4 times a. So if our goal is to isolate a, we need to do the inverse of multiplying by negative 4, which would be to divide both sides by negative 4. Negative 4 divided by negative 4 gives us 1, and 1a is a. So we achieved our goal of isolating a. These are the same signs, so according to spun, we get a positive answer, 8. If I were to check this, I plug in 8 for a, and I get that negative 32 equals negative 32. And finally, number 5, we have our n, and we're dividing by negative 5. The inverse would be to multiply both sides by negative 5, which you can think of as negative 5 over 1. The reason for this is because I could divide both of these by negative 5 when cross-reducing and end up with 1. 1n over 1 would just be n. So now I isolated the variable, and I get that 20 times negative 5 is negative 100. To check our answer, I have negative 100 divided by negative 5 equals 20. A negative divided by a negative does give us a positive. If I do 100 divided by 5, I do get 20. So n equals negative 100. Now let's practice some problems with fractions. If I have negative 1/3 w equals negative 2/7, and my goal is to isolate w, I have to think of which inverse operation I should use. Well, here we are multiplying negative 1/3 by w. The inverse of multiplying by negative 1/3 is dividing by negative 1/3. So let me say that again. Right now, we are multiplying w and negative 1/3. So I need to divide both sides by negative 1/3. Now, if you recall, when we divide by fractions, we actually can multiply by the reciprocal. Think about what you've learned in pre-algebra when you're dividing by fractions. Don't you multiply and flip the second fraction upside down? You're multiplying by the reciprocal. So, we're going to take our equation and multiply both sides by negative 3 over 1. Now, as we just learned with our properties of real numbers, there was the inverse property of multiplication, which stated that when you multiply a fraction by its reciprocal, or multiplicative inverse, you get 1. Negative 3 over 1 times negative 1 over 3 gives us 3 over 3, or 1. And 1w is just w. So by multiplying by the reciprocal, we were able to cancel out the fraction and get our variable alone. Now on the other side, I check to see if I can cross-reduce, which I can't in this case, so I multiply straight across and get 6 over 7. So w equals 6 over 7. Now when I check this, I have negative 1/3 times w, which we said is 6/7, and I want to see if that equals negative 2/7. Well, I can cross-reduce, so 1 and 2, and I do get negative 2/7. So our plan worked. You try number 2, so pause the movie and resume when you're ready. For number 2, we're multiplying x by 9/10. The inverse would be to divide by 9/10 or multiply both sides by the reciprocal, 10/9. These all cancel and give us 1x or x, and now I'm multiplying negative 9/15 times 10/9. Well, I can cross-reduce to get negative 1 and 1, and then here I can divide by 5 and get 2 and 3. Negative 1 times 2 is negative 2 over 3 times 1 or 3. So x equals negative 2/3. Now to check. I have 9/10 times negative 2/3, which should hopefully equal negative 9/15. I cross-reduce. And I get negative 3/5 equals negative 9/15. Now don't let this confuse you, because negative 9/15 is not reduced. So when I reduce it, and I divide both the numerator and the denominator by 3, I do get negative 3/5. So this worked. X equals negative 2/3. Now number 3. I have x plus 1/2, which equals negative 3/4. So we are adding 1/2 to our x. The inverse would be to subtract both sides by 1/2. Positive 1/2 and negative 1/2 cancel. Now I have negative 3/4 minus 1/2 equals x. Now don't forget that in order to add and subtract fractions, you need a common denominator. So my common denominator would be 4. So I can multiply both my numerator and denominator by 2 here and get negative 2/4. Negative 3 minus 2 gives us negative 5. We keep our denominator. So x equals negative 5/4, or x equals negative 1 and 1/4. Now, when I check my answer, negative 3/4 equals, I am going to write it as my improper fraction when plugging it in, because that'll be easier to actually add with. So I have negative 5/4 plus my 1/2, which is 2/4. And I do get that negative 3/4 equals negative 3/4. So that worked. Now, number 4, we have negative 1/3 plus x equals 2/3. Pause the movie and determine what you think you should do for number 4, and resume when you're ready. Now number 4 is tricky, because even though this says we're adding, and therefore some students think you need to subtract from both sides, we are going to be subtracting negative 1/3, which would be like adding 1/3 to both sides. If it helps, you can rearrange these terms so that you have positive x minus 1/3. And now, maybe you can more clearly see that you need to add 1/3 to both sides. Negative 1/3 plus 1/3 cancels out, so we're left with x equals 2/3 plus 1/3, which is 3/3, or 1. Now I can check this. Negative 1/3 plus 1, or 3/3, equals 2/3. 2/3 does equal 2/3, so therefore x does equal 1. Pause the movie to try number 5 and resume when you're ready. X plus 8.4 equals negative 3.9. Now, we're adding 8.4 to x, so the inverse would be to subtract 8.4 from both sides of the equal sign. These cancel. Same sign, so I'm adding and keeping. 8.4 plus 3.9 gives 12.3, and I keep my negative sign. So x equals negative 12.3. To check this, I plug in negative 12.3 for x. These are different signs, so I subtract 12.3 minus 8.4. Don't forget to line up the decimals. I need to borrow and borrow again. And then I have to take the sign of the higher number. So I get negative 3.9 equals negative 3.9, which does work. So x equals negative 12.3.